So first of all, I would like to thank organizers for a very kind invitation. And today, I would like to talk about exchange interaction at superconductor ferromagnet interfaces. And I think everyone here knows, but magnetic field, so magnetic order exchange field can penetrate into a superconductor, and that can potentially create an unconventional superconducting states like this spin polarized triplet superconducting states. And also, order parameter of a superconductor can penetrate inside a ferromagnet, and that can potentially modulate magnetic properties. And today I would like to talk about this kind of nanoscale exchange interaction at superconductor ferromagnet interfaces. And I'm a postdoc working in Professor Jason Robinson's group in Cambridge. And we are mainly focusing on superconductors and ferromagnets and strong spin-optic coupling materials as well. And today I would like to mainly talk about the results I got with Mr. James Devine Stoneman and Dr. Angelo Di Bernardo. He's now working in University of Constance in Germany as an associate professor. And also I'd like to thank collaborators here and also the financial support from EPSRC and Royal Society and international collaboration Oxide Super Spin Project. And I would like to first remind you how to create triplet pairs at SF interfaces. So we need this kind of nanoscale interface to create triplet Cooper pairs. If we prepare this kind of, for example, niobium iron SF structure, proximity effect happens and basically Cooper pairs leaks into ferromagnet and it's short range because exchange field kills antiparallel singlet Cooper pairs. But we insert additional ferromagnet with misaligned magnetization. Then basically this inhomogeneous magnetic exchange field from two ferromagnets convert these singlet pairs to triplet pairs. And once this is converted, so spins are already aligned for triplet pairs. So it is kind of robust against the exchange field of ferromagnets. So we can observe a long-range penetration of Cooper pairs inside a thick ferromagnetic layer. So if we prepare another superconductor here, we can observe long-range Josephson current. So we can make the thick ferromagnetic layer superconducting. And this method of creating triplet pairs were basically demonstrated, experimentally demonstrated around 2010. And this is an experiment of Dr. Kaiser and Dr. Anwar. And they observed long-range penetration of triplet pairs into a chromium dioxide. So this is strongly polarized ferromagnet. So this is a half metal. And distance is more than 1 micrometer. So this is long-range supercurrent through this very thick ferromagnetic layer, which can be explained only by triplet pairs. And this is Jason's experiment from Cambridge, and he used magnetization misalignment of chromium and cobalt, and he observed long-range triplet supercurrent inside flowing through a very thick cobalt layer. And this is from Professor Norman Burgess' group, Michigan State University. And he used misalignment of copper nickel and cobalt and observed long-range Josephson effect. And recently, we are using chromium iron interfaces because this is convenient structure. So as you know, iron is of course ferromagnet and chromium is kind of weak ferromagnet, weak antiferromagnet. And at this interface, spins are randomly oriented and frozen. So we have so-called spin glass state at this interface, and magnetization here is intrinsically inhomogeneous. So if we inject singlet pairs to this interface, we can convert spins from antiparallel to parallel. And if we prepare this kind of structure, we can observe long-range Josephson current flowing through thick iron layers. And we make this kind of device using conventional simple sputtering, magnetron sputtering method and focused ion beam patterning. And we deposit layered structure on silicon dioxide substrate. And here black region is silicon dioxide. And we have thick niobium, top and bottom niobiums. And we cannot see from this SEM image, but there is a thin magnetic layers, chromium and iron chromium in between the middle. And if we pattern this film from, using FIB, so we make side two cuts here and here. And then we can force the supercurrent to go through this magnetic barrier layer. And then we can observe Josephson property of this magnetic Josephson junctions. And here, this is a long-range Josephson current of this chromium, iron chromium Josephson junction. And we can observe large supercurrent even if iron layer is quite thick. And this is the decay of Josephson current as a function of iron thickness. And this dashed line is the trend for singlets. So without spin glass, without converter, so we don't have chromium here. In this case, 4 nanometer or 5 nanometer are the maximum to detect Josephson current. But if we insert chromium pair converter, then we can observe large supercurrent even for 13 nanometers thick iron samples. So recently, we are more focusing on the physics of this long-range Josephson current itself rather than just a creation. And I would like to today show the results of this structure. So here it's a bit complicated, but we have another superconducting niobium inside the Josephson junctions, long-range Josephson junctions. So here, this niobium is normal conventional singlet superconducting state because we don't have converter between this iron and central niobium. And we can expect a totally different trend for singlet supercurrent and triplet supercurrent in this Josephson device. And if we prepare very thin iron layers, then singlet supercurrent can penetrate through this device as well. And in this case, if singlet supercurrents flow through this device, usually supercurrent doesn't decay in a superconductor. So, for example, even if we increase the thickness of this superconducting barrier, singlet supercurrent shouldn't show a decay. But if we increase the thickness of iron and if we block the singlet component, then we can extract the behavior of pure triplet supercurrents. So this is the experimental results. So we have devices with thin iron layers and thick iron layers. So this left figure shows the trend for singlet supercurrent as a function of niobium interlayer thickness. And this right one is the trend for triplet. And I would like to explain from this left figure. So we deposited many samples with different niobium interlayer thickness. And here niobium has two regions, non-superconducting region and superconducting region. And when this niobium interlayer is thinner than 25 nanometer, it doesn't become superconducting. So it's normal state niobium. In this region, if we increase the thickness of this niobium interlayer, singlet supercurrent slowly decreases. So slowly it shows a kind of very slow decay. That is simply because barrier layer, non-superconducting barrier is becoming thicker. But once the interlayer becomes superconducting, we can observe a significant enhancement of this supercurrents. This is because interlayer of niobium basically forms a Josephson coupling with top and bottom electrodes. So we have effectively two Josephson junctions in series here. And that basically reduces the thickness of barrier layer compared with this single Josephson junctions. So this formation of double junction basically enhances singlet Josephson current. But if we block singlet component by preparing a thick iron layer, then we can see a totally different trend. So in the normal state, we can see a very sharp suppression of this long-range triplet Josephson current. And we think it is related to spin scattering because triplet pairs are spin polarized and it's sensitive to spin scattering. And here, in this superconducting region, interesting thing is we cannot observe any enhancement of supercurrent, which means triplet pairs, long-range triplet pairs cannot mediate Josephson coupling with a singlet superconducting barrier here inside. So superconductivity of this interlayer can be confirmed by RT curve, but resistance doesn't go to zero. So it doesn't create kind of double Josephson junction behavior. So this means that basically triplet pairs cannot mix with singlet wave function, and they have a kind of independent superconducting condensation states. And this result is now on arXiv now. And as a second part, I would like to also talk about oxide SF interface proximity coupling. And this is mainly the results I got with Dr. Angelo Di Bernardo. And Angelo and I have tried many combinations of materials, SF materials. And we mainly focused on the penetration of magnetic order inside a D-wave superconductor, which we call an inverse proximity effect. So inversely, magnetic order can penetrate into a superconductor. And that can basically spin split the quasi-particle density of states and suppresses TC of the superconductor. And this length scale is typically around the coherence length of a superconductor. And we can detect this inverse proximity effect from just a simple transport measurement, for example, bilayer of aluminum europium sulfide, so superconductor ferromagnetic insulator bilayer structure. So just an important thing is to match the length scale of coherence length, diameter of Cooper pairs, and domain wall width of ferromagnetic insulator. So if you match these two length scale, what you can see is on a domain wall region, so of course exchange field is rotating, and if it is a length scale of coherence length, basically Cooper pair can experience an averaged exchange field. So if it is rotating, effective exchange field here is reduced. So if this inverse proximity effect is strong enough, we can see a TC difference between here and here. So TC on domain wall and TC on homogeneously magnetized domain should be different. So Professor Jagadish Munira's group observed this effect using this bilayer structure. And they measured RH at around the onset superconducting transition temperature. And they observed the drop of resistance. Drop of resistance means increase in TC because they are measuring around the superconducting transition. So they observed increase in TC at the point where the domain wall density is maximized, so around the coercive field. And we observed something similar for oxide superconductor as well. So we had to prepare electron-doped cuprate superconductor to observe this kind of inverse proximity effect. That is because we needed to prepare a material with long in-plane coherence length. So this is 10 times longer than the hole-doped type cuprate. And this is close to the typical domain wall width of ferromagnetic insulating manganite. And we used PCMO as a ferromagnetic insulator and observed this TC switching. And we couldn't observe this effect for YBCO because YBCO has a short in-plane coherence length. But if we prepare out-of-plane exchange coupling structure, so if we prepare tri-layer structure, we observe the very large TC switching. So here we have two ferromagnets, so we can control the exchange field along the out-of-plane direction. And depending on the magnetization orientation of these two ferromagnets, we can control the amplitude of exchange field inside YBCO. And we can observe a big TC shift using this structure. So this 1.7 Kelvin is kind of the biggest TC shift we can get from this kind of FSF spin valve structure. And this coupling, exchange coupling, is quite strong. And this effect, TC switching, survives up to about 20 unit cells of YBCO. So this is TC switching as a function of YBCO interlayer thickness. And this is actually an unconventional effect because if we use S-wave superconductor, for example, niobium, we cannot observe TC switching if niobium becomes thicker than its coherence length. And this is more than 50 times thicker than the coherence length of YBCO. So this exchange interaction is unconventionally long range. And we are thinking it is related to the D-wave pairing symmetry of cuprate superconductors. And D-wave pairing symmetry has a nodal region where the gap is very small and coherence length is how to say, effectively long, very long. And we are thinking pairs and quasi-particle excitations around these nodal regions are playing an important role in this long-range exchange interaction. And details are basically discussed in this paper. And we can also observe this effect at a temperature far below TC. And we did density of states analysis. And we used grain boundary substrates because we don't have helium-ion focused ion beam machine. And basically it's sandwiched by thick two ferromagnets, and it's difficult to use, for example, STM to measure the density of states of superconductor inside a superconducting spin valve. So probably this grain boundary method is the only one method to measure density of states of this kind of structure. And what we observed here is parallel states gives a very strong enhancement of density of states and the superconducting gap. So this is IV and DIDV of this tri-layer structure. So we need to apply large external field to make these two PCMO layers to parallel, but nevertheless, it increases density of states and superconducting gap. And this enhancement roughly corresponds to removing external field from 5 Tesla to 0 Tesla. So we can observe such kind of big enhancement by applying field. I mean, using this strong exchange interaction. And this coupling is quite strong, so we can also observe the opposite effect. So we measured MH of this device with several different temperatures. And basically, two PCMO layers show similar magnetic properties. And at above TC, it behaves like a single ferromagnet. This is MH curve. But if you decrease the temperature and if you go below the TC of YBCO, so we can start to see independent switching of two PCMO layers. So YBCO interlayer here wants to align the two PCMO layers to become antiparallel. So superconductivity of YBCO is here creating an antiparallel phase of these PCMO layers. So if we use this kind of exchange interaction, we can basically switch, for example, potentially we can switch magnetization of ferromagnet using superconductivity. And this is a summary of my talk. Thank you. Thank you for your very kind attention.